my dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda. I'd like to welcome you all to our International Physics webinar. So today it's our 30th webinar. Uh, good afternoon to all. Hope you are well and safe from Corona pandemic. So all we know that we are staying in a Corona pandemic situation, and as we cannot continue our normal academic program in our institution, so we have to start our online program. So our Department of Physics have already started some online program like online classes and online international physics webinar. So we are actually in a situation, the new experience all of we are having, because we have to follow some rules, health rules and something. So this is new normal, and we are trying our best to adjust with this new normal. And we have arranged the series of online physics webinar, and in those physics webinar, physicists from different countries are coming as a main speaker, and they deliver their speech, and they share their experience, they share their knowledge with our student. And by this way, I think students have benefited. So this is I think for a student, it's an opportunity to interact with famous physicists. The aim of our webinar is to actually motivate our students and to encourage them in this Corona pandemic situation. So I'm happy to share with you all that. We have successfully completed 29th webinar, and today is our 30th webinar, and I'd like to thank all for all of your support and encouragement in this regard. So today I'd like to welcome you all to a joint session between Pabna University of Science and Technology, Pabna, Bangladesh, and Istanbul Technical University, Istanbul, Turkey, in higher energy physics and astrophysics. And we have with us here today Dr. Kazim Yavuz Eksi, Professor, Department of Physics Engineering, Istanbul Technical University, Faculty of Science and Letters, Istanbul, Turkey, joining us from Turkey, and he has already connected with us. So I'd like to welcome him. So good afternoon, sir. And
good afternoon.
Welcome to our webinar, and welcome to our university and Bangladesh.
I thank you for the invitation. I'm going to be introducing you some of the most interesting objects. They are called neutron stars. They are called sometimes superstars of nature. I'll explain why. First, I'd like to introduce you my group of students here. I'm the only astrophysicist in the department, and this is our laboratory, and we have a computer down here and nothing else. But we have very enthusiastic students. They're very good, and so we have no excuse for doing good science. I call this Pines theorem. David Pines, in 1990, in a conference, he suggested that neutron stars are superstars. Why is he calling them superstars? Here is the proof. They are born in supernova explosions. They are super dense objects. The density reaches somewhat like 10 to the 15 grams per centimeter cube. They can attain super spin frequencies. For example, they can rotate about 1,000 times about their rotational axis. And they are super precise clocks. That means you can predict. I mean, they are better than best atomic clocks we can devise on the Earth. And they contain neutrons in a superfluid state in their crust. And they have the protons in a superconducting state, again, inside and in the crust. And they can experience superquakes. If you are to compare it with the Richter scale, they are experiencing somewhat like 17 Richter magnitude quakes. And neutron stars can have super strong magnetic fields. Typically, they would have a magnetic field about 10 to the 8 Tesla, but some of them can have 10 to the 11 Tesla of magnetic fields, which is beyond the quantum critical limit. And they are super accelerators. So their magnetosphere rotating so rapidly with so strong magnetic fields, it would be a very good site for accelerating particles to super high energies. So let's review some facts about neutron stars. A typical neutron star would have a mass about 1.4 solar masses or somewhat higher, up to 2 or 2.5 solar masses. We don't know the maximum possible limit actually. It would be about 2.5. On the other side, they would be very small objects. They would have a radius about 10 to 15 kilometers. The best estimate today is about 11 kilometers. So given these two numbers, you can estimate the average density of a neutron star. It would be about 10 to the 15 grams per centimeter cube, which is beyond the density of nuclear matter on the Earth. And as I told you, the magnetic fields can be typically 10 to the 8 Tesla, which is equal to 10 to the 12 Gauss. But some of those neutron stars, which we call magnetars, they have magnetic fields even exceeding this super high fields. So they would have magnetic fields about 10 to the 15 Gauss, which is equal to 10 to the 11 Tesla. And they would show some bizarre phenomena. So, for example, they would explode. They would show explosions where the magnetic field lines reconnect. And these explosions would reach energies like 10 to the 46 ergs per second. We call these giant flares. One of those happened in 2004, December 2004, and then it caused some ionization at the outer layers of our atmosphere, while the object was already 50,000 light years away. If the object was only 50 light years away, then our atmosphere would be blown apart. I mean, it would just, evaporate. So why are neutron stars important? Are they related to fundamental physics somehow? Yes. We don't know the ground state of this dense matter. So understanding the ground state of dense matter is an important aspect of fundamental physics. And of course, another thing related to neutron stars would be that they would have very strong gravitational fields. So you might like to test Einstein's relativity with neutron stars. Yet another aspect, well, here you see two objects, for example, two neutron stars rotating about each other. According to Einstein's general relativity, this system would lose orbital energy and approach each other while emitting gravitational waves. and that is how they would do this according to general relativity, and it was tested by Hulse and Taylor in 1974, and they were given the Nobel Prize in 1983. And more recently, we have witnessed the merger of two neutron stars that have approached each other in this way by releasing gravitational waves for a long time. So the final stage happens very rapidly, and it is observed as a gamma ray burst. And associated with the gamma ray burst is the emission of gravitational waves, which were detected in 2016, very recently, and that was also awarded the Nobel Prize. Another aspect of neutron stars related to fundamental physics is the superfluidity in them. Well, on the Earth, in terrestrial conditions, you can produce superfluidity only with helium, right? You would just cool the helium below the lambda point to obtain the superfluidity of helium, because helium is the only element that remains fluid at such cold temperatures. Well, in neutron stars, neutrons would be in a superfluid state. And as you well know, a superfluid cannot rotate, and it forms these vortices to keep or to conserve the angular momentum, right? So the sum of the angular momentum of the vortices would be equal to the total angular momentum of the neutron stars. So these vortices would be moving inside a neutron star, and they lead to interesting observational phenomena, which we call the glitches, which are the jumps in the spin periods. So, how do they form? How do the neutron stars form? As you well know, there are three possible end products of stellar evolution, and these are all compact objects. Whichever a star will evolve into depends on the mass of the progenitor, the chemical composition of it, and the angular momentum. So if small mass objects, they evolve into white dwarfs at the end of their lives. Objects with masses in the mediocre range, like 3 to 8 solar masses, they would evolve into neutron stars, and the most massive objects are expected to evolve into black holes. Here you see a supernova remnant, and this is the death of a massive star which lived some time ago. It was observed as a supernova explosion in Adonis 1054. That means after Christ, 1054. Chinese astronomers registered this event as a guest star. So they didn't know it was a supernova explosion. And actually, they have been observing such objects occasionally, and they have registered them as guest stars because they would appear in the night sky. They would be there for a few months, and then they would disappear or decline gradually. So they were why they're calling these guest stars. And in the 20th century, we have understood that they are associated with neutron stars. They are associated with the birth events of neutron stars. So in the beginning, I told you the neutron stars are born in supernova explosions. That means when the nuclear reactions in a star end, and you finally have an iron core, you don't have any place to go by nuclear reactions, because iron is the most stable of the elements. So you cannot generate energy. What happens is that the iron core collapses to form the neutron star, while the other layers are ejected with this huge explosion that we call the supernova explosion. Actually, lots of neutrinos are emitted. 99% of the energy is emitted in the form of neutrinos. And what we see as a supernova in the optical is just a tiny fraction of the total energy emitted. So at the center of this nebula, we have discovered a pulsar, and which means it's a neutron star which are showing pulsations because each time it rotates, the magnetic pole aligns with our line of sight, and we see a pulse. Okay, so there's nothing pulsating actually. It's just rotating, and there's a magnetic pole which we can see, and if this pole is passing from our line of sight, we see a pulse. So these pulses were discovered from a neutron star right at the center of this Crab nebula. So we know the exact date of this because Chinese have registered this as a guest star. Now the neutron star at the center is rotating with a period of 33 milliseconds. So it's rotating 30 times about itself. And it is slowing down at a slow pace, 4.22 times 10 to the minus 13 seconds per second. So it's about microseconds in a year. So it's slowing down, and we can measure it because measuring time is very easy in astrophysics. And these objects are very good clocks. Actually, we can measure the period of this object up to a precision of 10 digits. So this is slowing down, and all this energy emitted by the neutron star is actually the conversion of this kinetic energy, rotational kinetic energy of the neutron star to electromagnetic radiation. So this is the spin down power minus I omega dot is the rotational power of this object. Omega is the angular frequency, and omega dot is its rate of change. So if you plug in the numbers from the periods, okay, 2 pi over p is the omega, all right? Then you can convert p dot as well to omega dot. You would get a luminosity like 10 to the 5 times the solar luminosity. So look at this. The object is slowing down at a rate of microseconds in a year, but this is still corresponding to a huge power, which is exceeding the nuclear power of the sun by 5 orders of magnitude. So why are they slowing down? Because a rotating object, a magnetized rotating object, of which the rotation axis and the magnetic axis are not aligned, it would emit energy by magnetic dipole radiation. So the magnetic dipole model says that the rotational power would be proportional to the angular velocity to the fourth, right? And so mu here is the magnetic dipole moment, and alpha is the inclination angle between the rotation and the magnetic axis. So there is a torque acting on the neutron star due to this magnetic dipole radiation. And actually, you can see how they are slowing down. You can look at thousands of pulsars detected since 1997. We have 2,500 of them. And you want to measure the breaking indexes of these objects. What is the breaking index? It is defined as omega times the second time derivative of omega divided by omega dot square. So this is a dimensionless number, but it's hard to measure this because the second derivative is hard to measure. It is hard to measure because although these are very good clocks, there's still some noise in their spin down due to this superfluid events inside. And it makes it very hard to measure the second derivative. But anyway, it was possible to measure it for some objects. We will see. But by the way, if this magnetic dipole model is correct, then what you're expecting is that the breaking index of pulsars should be 3, because if you plug in this into here, you get 3. But the measured breaking indices are as follows. For example, in the Crab pulsar, you measure it to be 2.5. Here are some others. You see some of them really approach 3. Let's say you have a 2.8 here, 2.65, 2.7. But some of them are really, really far from being equal to 3, all right? And some of them even change, all right? Look at this. This was once 2, then it approached 0. The second most famous pulsar, Vela pulsar, has a breaking index of 1.4. And one of the objects have a breaking index exceeding 3. So how is that possible? There had been some suggestions why the breaking indices are generally less than 3. Some suggest that there's an ejection of relativistic particles along with the electromagnetic waves. That is a possibility, of course. Some suggest that the moment of inertia of the neutron stars are changing, because as the star is cooling down, the superfluid region in the crust is enlarged, and the outer crust, which is decoupled from this, becomes thinner and thinner. And so the effective moment of inertia changes in time. And some suggest that the neutron star is not a point dipole. So if you consider a finite dipole, you can explain this smaller than 3 breaking indices. Some suggest that the inclination angle between the rotation and magnetic axis are changing. So you assumed it to be constant. So there's going to be some change due to this. And some suggest that the magnetic fields of neutron stars are growing in time, and that would also change the breaking index from the estimate of 3. So there could be some different reasons why the fields could grow. Some suggest that thermoelectric effects lead to the growth of the field, and some suggest thermomagnetic processes. And some others suggest the following. there is a rediffusion of the field to the surface after the field of the neutron star is buried by some fallback matter. Remember, the neutron star would burn in a supernova explosion. And all supernova explosion simulations show that some of the matter expelled in the explosion cannot reach the escape velocity and falls back. And when it falls back, it just buries down the magnetic field of the neutron star, and then the field diffuses to the surface in time. That is just a hypothesis, and these guys have suggested these. And actually, we have shown not very conclusive evidence for that with my master student, Abdullah Güneydaş. So our work is a bit of work joining the observational results, the break-in indices, and the space velocities of pulsars. So when a neutron star burns in a supernova explosion, it also gets a kick from the explosion. So we observe the neutron stars have velocities like 500 kilometers per second. So these are the space velocities, and these are very high. If you look at the progenitors of these stars, they are just moving with velocities like 30 kilometers per second. So why would they have, 300 kilometers per second? Because they get a kick in the supernova explosion process, because the explosion is not spherically symmetric. So if the neutron star has a high velocity, then it would suffer less fallback material, and so its field would be buried at a lower level, and then the field would diffuse more rapidly. So we have related these two observations here, and it supports the rediffusion of the field. But also a good explanation would be that Line et al. Observed the increase in the inclination angle. That's also compelling. That could explain why the break-in indices are less than 3. Okay. So let's look at the hydrostatic equilibrium of self-gravitating spherical objects. So you have a mass conservation equation and a hydrostatic equilibrium equation where the gravitational acceleration is gm over r squared. And so you would have an equation of state, but this equation of state is relevant for ordinary stars. This is the gas pressure of ions and the gas pressure of the electrons, and then the radiative pressure of the photons. So this is the equation of state of ordinary stars. And these two equations govern the structure. But you know that degeneracy would become important if the particles in the star are condensed into tiny regions. The first, it happens with the electrons because they would have the largest de Broglie wavelengths. So when the mean separation between the particles become comparable to the de Broglie wavelength, you would have the degeneracy pressure becoming important. So as a star evolves in its lifetime, its core would become more compact after each nuclear reaction. For example, now the sun is burning hydrogen. It is not burning helium at the moment, right? Because the core of the sun is not sufficient for ignition of helium into carbon, right? So only after hydrogen in the core finishes, the core will contract and become hotter, and then the fusion of helium into carbon will start. So you would have a more dense core in that case. And then you would have the next reaction in higher mass stars, and the core would become even more compact. For low mass stars, at some stage, you cannot pass to the next reaction because the degeneracy pressure sets in before the core can contract to ignite the next reaction. So here are some scaling relations. The mass conservation implies that the central density would be proportional to the mass and inversely proportional to the radius q. And hydrostatic equilibrium implies that the pressure is proportional to the mass squared divided by the radius to the fourth. And if you have, a white dwarfs, right, which are objects held against gravity by their electron degeneracy pressure, as first suggested by Howard Fowler, then you would find that the Fermi energy goes with the number density of electrons to the power of 2 over 3. And if then the central pressure would go with the central density to the power of 5 over 3. And using those scaling relations, you can just see that the radius of white dwarfs would be inversely proportional to their masses, and it goes with mass to the power of minus 1 over 3. So a more massive white dwarf is more compact, as you see from here. Why is this so? You can understand it from the origin of the pressure, right? Electron degeneracy pressure is there because when you try to squeeze the electrons into a tiny region, the electrons start to jiggle faster, right? And this is due to quantum mechanics, basically, right? Heisenberg's principle says that if the location is well determined, the momentum is underdetermined, right? So if you have the electrons in a tiny region, that means they would be moving faster. And so if you increase the mass of the object, then its gravity is more. So in order to resist this gravity, the star has to increase the pressure. And the way to increase the pressure is to become more compact. And as you well know, Chandrasekhar in 1931 understood that if you have more massive white dwarfs, then the electrons would become so rapidly moving that they would be moving with some velocity close to the speed of light. And so, for example, when they are moving with the 99% of the speed of light, and if you increase the mass more, the gravity increases, right? But the electrons cannot go faster. So how can they balance the gravity? So they cannot. So there's a critical maximum mass of white dwarfs, and it is a relevant number. It's 1.4 solar masses. Then the question naturally arises: why? What happens to stars with cores exceeding 1.4 solar masses? At the time of Chandrasekhar, he didn't have a good answer to this. He just said, one has to speculate on other possibilities. That's how his paper ends. But if you, today we have better answers to this. Okay, now you see this Chandrasekhar limit here. So if you have a higher mass white dwarfs, then there would be a maximum to the mass of the white dwarfs. But before this Chandrasekhar limit, which is reached asymptotically, takes over, there is a process, the physical process, which we have to consider. This is called the neutronization. It was also understood in 1930s, right? So you know that there's a beta decay process where a neutron would decay into a proton and an electron and an antineutrino. This happens if the neutron is isolated in the terrestrial conditions. And in a degenerate gas, the reaction would be suppressed. So it doesn't happen in the nuclei. Now, in a neutron star or in a dense region, it doesn't happen easily as well. So there's an inverse process of this, where an electron would meet with a proton and would produce a neutron and a neutrino, right? So this process would lead to the taken away of the electrons in the white dwarf if the core of the white dwarfs become too dense or more massive, right? So the electrons would be very relativistic and they would tend to merge with the protons to form neutrons. But remember that pressure was produced by the electrons. So if the electrons are converted into neutrons, then you don't have much pressure. So you increasing the mass of the object, but the pressure is decreasing. This is an unstable situation. So this brings the upper mass of white dwarfs actually. If you can do this in a ultra-relativistic case for a proton, electron, neutron gas, you would find it as a beta equilibrium case where the electrons have 1 unit, protons are 1 unit. So for charge equilibrium, that should be the case. But the neutrons would be dominating. So they are 8 times larger than protons and electrons. So here we see why we would have neutron stars. But of course, the neutron star is not a gas of electron, proton, neutron. They have iron nuclei there. But you can see that the nuclei would be neutron dominated. So this is not a situation you meet in the terrestrial conditions. In the terrestrial conditions, you find that the number of neutrons and protons are almost the same, right? So the effect of neutronization on the mass radius relation of white dwarfs were studied here. Now, there is another thing we should consider when we are reaching these maximums. That's the relativistic corrections to the hydrostatic equilibrium. In general relativity, the hydrostatic equilibrium has corrections. These 1 plus p over rho c squared is a relativistic correction. The other terms are also relativistic corrections. In Newtonian gravity, you only have this one. Okay, the mass equation doesn't change, but this is just on the form. In reality, actually, this is not a spherical. In general relativity, the spherical shell would be described rather differently, of course. Okay, so whichever comes first, GR instability or beta instability. Well, GR is also causing instability. Let's try to understand this. Now, in Newtonian gravity, you see that the pressure gradient balances the gravity of the object, right? But you see that in general relativity, you have pressure on the right-hand side contributing to the gravity. This is understandable because in general relativity, all forms of energy contribute to the gravity. So pressure is a form of energy, right? Because it's just a random motion of the particles. So if the star is squeezing and it's increasing its pressure to balance gravity, then there could be a limit where the pressure is so high that it's actually increasing the gravity, and so this ends the static equilibrium of the star. So it depends on the chemical composition, whichever comes first. In some cases, general relativity instability would come first. In some cases, the beta instability would come first. So it was studied in Rotondo et al. So in hydrostatic equilibrium, there could be two static equilibrium. So the white dwarf case, where the radius is larger, so this is the stable branch here. And for the neutron stars, you would go here. So this is an unstable branch. It's not realized in nature. So white dwarfs are some stability region, and neutron stars and another stability region. Also, we should see that there's a phenomenon called neutron drip, because as more neutrons are created in the nuclei, the energy levels for the neutrons get filled up to an energy level equal to the mass of the neutron times the c square. And at this point, any electron that penetrates the nucleus will create a neutron, which doesn't tend to stay in the nucleus, but tends to drip out of the nucleus. So we call this the neutron drip limit. And from this onwards, the neutrons, the density of neutrons freely available increases. And eventually, as you go deeper in the neutron star, all the neutrons would drip out of the nuclei, and we would have a totally neutron fluid interior of the star. And this is how the density distribution goes. You see it's changing by 15 orders of magnitude near the crust. And this is how the pressure goes. And these are the equation of state. So we have in Akmal-Pandra-Handy equation of state. We assumed for the solution. We don't know the exact equation of state in the center, by the way. And this is Negalev-Water equation of state in the inner crust, and Baim-Pedig and Sutherland equation of state in the outer crust. So this would be the mass distribution in the star. So near the crust, it would be somewhat constant. And this is the total mass versus total radius for different equation of states. So there's a huge plethora of equations of state which make different assumptions about the composition of the star and the interaction of the nucleons. So you have different mass radius relations resulting from this. But there are some constraints on them. For example, there's a two solar mass object detected. So any equation of state should be able to produce neutron stars with masses exceeding this observed mass. For example, this equation of state, MS1, or this equation of state, FSU, would have trouble with this observation because the maximum mass attained with this equation of state is less than 2 solar masses. But already we have observed a neutron star with a 2 solar mass. So this favors these equations of state. But still we have many equations of state about 2 solar masses. So which of them is correct? So we should also be measuring the radius of the neutron star. And this is a bit hard to do. And this is how this was observed. Anyway, here are some observations by Guer et al. And they are placing constraints also on the radius of a neutron star. And so these are their measurements. So they show that this 10 kilometer is a reasonable radius. These equations of states were calculated, or these ones were calculated, assuming that general relativity is the final word on classical relativistic theory of gravity. Okay, but you know that there are other theories of gravity which are relativistic, and they can make reasonable predictions about the solar system, but the predictions for neutron stars could be different. Okay, neutron stars could be used for testing these, of course. But still, general relativity presents us the fundamental framework for understanding gravity. You know this, of course, very well. The existence of black holes, the Hubble expansion of the galaxies, and many other observations are compatible with the predictions of general relativity. But I'd like to show you this graph. SS is the solar system, okay? So most of the best tests of general relativity were made in the solar system. And here on this graphics, the x-axis is the compactness, which is gm over the radius times c square. So how compact the objects are. So the solar system, in the solar system, the compactness is given here, but the compactness of neutron stars is about 5 orders of magnitude larger. And the y-axis is the curvature. Okay, so it means that the curvature, space-time curvature, in a neutron star would be some 14 orders of magnitude larger than the solar system. Okay, so any theory of relativistic gravity which can make similar predictions with GR at the weak field limit can have different predictions for the systems of neutron stars where the curvature is much higher. So the strongest field solar system tests would be probing compactnesses like 10 to the minus 6 and curvatures like 10 to the minus 28. And you see these Hall-Taylor and neutron stars, Hall-Taylor pulsar, they are so separated from each other. And neutron stars and black holes. Okay, the LIGO experiments would be are occupying this region. Yeah. Now, in a neutron star, you'd have compactnesses 5 orders of magnitude larger and curvatures 15 orders of magnitude larger. And you see, remember, these are relativistic objects. Okay, so these are all relativistic corrections, the colored ones. So we can use neutron stars to find deviations from general relativity, or at least we can put limits on such theories by using neutron stars, the observed parameters of neutron stars. For example, you know that the FR, there's a bunch of theories called FR theories. One of these would have a function like R plus alpha R squared. So alpha equals 0 is the case of general relativity. Okay, and so let's assume there's a correction to this theory where, assuming this is R is just, FR is just a series, and we have just added one more term from the series. And how large could alpha be if, GR is a limit of such a theory? And actually, we have made this calculation some 10 years ago. And we have placed limits on alpha, as you see here, with my colleagues in Istanbul Technical University. Actually, they are string theorists, and this theory is somewhat motivated by string theory, where the constant there, of course, would have dimensions at the order of Planck units, so it's insignificant. But let's assume that it's just any constant. So how large this constant could be? That was the question we asked, and we have found that it should be less than 10 to the 10 centimeter square. And someone else, by using gravity probe B data, put constraints on the same value as large as 5 times 10 to the 15 centimeters square. So our value for our constraint is much more tight, simply because we are using neutron stars, right, which is very, very dense object compared to the Earth. We have also put some limits on another theory where there's another correction term, R mu nu, R mu nu. So this is the Ricci tensor, contractions of the Ricci tensor. Okay. Now, there are 3 different curvatures in general relativity. Actually, they are a measure for tidal forces, but because tidal force is the only sign of gravity that cannot be cast aside by a coordinate transformation. So the tidal force on a body moving along a geodesy could lead to a distortion of the shape of the body and a change in the volume of the body. So we have different curvatures in general relativity and in relativistic theories of gravity. The Riemann curvature tensor captures both of them. The Ricci curvature only captures the trace component of the Riemann tensor, and it only conveys the second one, the change in the volume of the body. And the Weil tensor, which is the traceless component of the Riemann tensor, conveys the information of only the first one, a distortion of the shape of the body while the volume is constant. So related to these, we have constructed these curvature scalars. This J square is R mu nu, R mu nu. So K square is the Riemann curvatures, mu nu rho sigma, mu nu rho sigma. And then we have calculated them inside the neutron star. So all these 3 different curvatures we have constructed. And then we have looked at how they are inside the neutron star. And we see that the curvature inside the neutron star is still very large. One would expect that as you go inside, the mass contained in a radius of r would become smaller, and so the gravity would become smaller. But as the radius is smaller, the curvature increases, because the smaller the radius, higher is the curvature. So the catch is that even at the very center of the neutron star, you have very strong curvature, which is beyond what is probed in the solar system tests. So this is another, this is a study suggesting that when you measure the mass and radius of a neutron star, you're not actually putting constraints on the equation of state. You're actually putting constraints on the gravity theories. And actually, I think I should stop here. If you have any questions, I would like to answer those questions.
Yeah, thank you, sir. So we have some questions. So we can discuss in our discussion session also. So which one you prefer?
Okay, sure. Now I see some people ask for the presentation slides. Well, you can write me emails. Of course, you can find me on, Googling my name, and I would send them.
I can add the question in the screen. You can see in the screen.
Some day ago, they published a news in Astrophysical Journal that was the dimming of Betelgeuse star. Hubble Space Telescope gave a reason behind this. Mainly, it was due to outburst of that star. My question is, what's the main reason of outburst? Well, whatever the reason, I think it's not related to neutron stars, and I don't know why this star shows the Betelgeuse. We are expecting that Betelgeuse will explode as a supernova explosion in the future, but we don't know when, right? But the dimming of it at the moment is something I don't know why.
Okay, we have another question. So as it told that the white dwarf will be more compact when mass increases, how could mass be increased in any star? Is it mass or density?
The density also increases, but I'm talking about increasing the mass. Actually, I explained it in my talk. The reason is the origin of pressure, right? The origin of the pressure is due to the electrons being squeezed in a tiny region. They are jiggling faster, right? This is a quantum mechanical phenomena. So if you increase the mass, you're increasing the gravity of the object. So in order to balance the gravity, the object should increase the pressure. And so in order to increase the pressure, it would squeeze the electrons in a more tiny region than the previous one. So if you have a white dwarf, which is accreting matter from a companion, as the mass of the white dwarf is increasing in this process, it will become smaller and smaller and denser and denser.
So maybe we have another question, the same person.
When any star becomes white dwarf or neutron star, then is there any change in the space-time curvature? Yes, the original star has a very small curvature and compactness, but when it becomes a white dwarf and a neutron star, the compactness increases by 5 orders of magnitude when it becomes a neutron star, and the curvature increases by 15 orders of magnitude. And we haven't tested actually general relativity at such curvatures yet.
Thank you, sir. So this may be the last question.
So we can assume from the radius of an exploding star which element would be generated at most. So backwards, we can also calculate from the exploded stars their radius from the element density in space. Well, we can find the element density in space, but it would not be very easy to go to the radius of the progenitor star from the elements. But astronomers can really estimate what type of star has exploded and at what stage it was. I mean, all these elements. For example, did it produce iron yet or not? Right? They can do this.
Okay, maybe this is the question up to now.
Of
So
course.
maybe you can continue. So maybe somebody have connected. So I'm asking if you interested to join, you can join. Mr. Shovik Brahmo. So can you hear me? If you have any question, you can ask. Hello, Mr. Shovik. Okay, maybe he's not connected with us. So thank you, sir.
I thank
for
you
your
for your
nice
invitation
presentation.
again.
Yeah. So I think a student have learned a lot of things, and actually we have also learned a lot of things, and we are very grateful to you because we know that you are too busy with your
It
research
was a
work
real
in this
pleasure for
corona
me.
pandemic.
Yes.
It's my pleasure and privilege to host you. And I'd like to say thanks on the behalf of the Department of Physics, Government University of Science and Technology. So, sir, if you are free, so we'll arrange another program in near
Of course.
future. So for our student. So thanks for everything, sir, for your support, for your cooperation, and it's really a pleasure, sir, to do webinar with you.
Goodbye.
So goodbye for today,
And
and hopefully we'll
and
see you,
greetings from Turkey
in near future.
and Istanbul.
So,
And best wishes
yeah.
from our department. Thank you for the invitation again.
Yeah.
And see you.
It's a pleasure. Maybe this is the first international webinar with any Bangladeshi university.
Yes, it is my
Is it,
first.
sir? Okay, so it's our pleasure. Yeah, it's really our pleasure, and we feel really proud to
Thank
host you. And thanks again. So hopefully we'll see you again very soon.
Bye-bye.
So bye for today.